In this video, we'll look at section 3.3, finally looking at the definition of a group and some examples. So a group is a set G, a set of elements G, together with some binary operation. Here we just use a little circle as our operation, but we'll see different things, like, of course, the plus sign, multiplication, symbol, a star, sometimes we'll use as our operation. Sometimes just simply concatenation of things. But what that operation does is takes two elements from the set G and brings it back to G. So you may have heard that, a group has to be closed. This is actually telling us that it's closed. We say that it has closure because the binary operation takes two elements from the group and does something to it, but brings you back to the group. So you can, like, if you tried to construct a group with, making sure it has all the other properties, you might forget about closure because you might not realize that your operation is actually sending elements outside of the group. But yeah, so the binary operation forces it to be closed, and this operation has to be associative. So if you have three things, A, B, and C, then the order of the parentheses doesn't actually make a difference. If you do A with B first and then C, it's the same as if you did B with C first and then A. But notice the order appearing from left to right is the same in both, so that's important. So if you had, a bunch of things on each side, as long as they appear in the same order, and you just evaluate in any order from that point, then we say that it's associative. A group has to have an identity element. So, in addition, the identity element is 0. In multiplication, it's 1. You have an identity matrix for matrices. You have an identity map when we were talking about our symmetries before. So it just has to essentially leave the elements alone. So if you do E with another element A, or do it on the other side, because we don't necessarily have commutativity here, you get back A. And every element has to have an inverse element, which we'll call A to the -1 for A inverse, where that if you do the binary operation with that inverse element, it's the same as if you did it in the other order, but in either case, you get the identity. So just staring at a Cayley table, if we want to decide if it's a group, it may be, like, associativity is definitely difficult to sort of notice in a Cayley table like this, but we can certainly see that this one's not a group because it doesn't have an identity element. There's no element that when I multiply by all the other elements, I get that element back. So in other words, visually on the Cayley table, I would need to see a B, C, D showing up here for any of these to be an identity. So we can quickly notice that this has no identity. Here you can see A, B, C, D showing up. And in fact, we've seen this one, or we will see this one as Z4. If I look at Z4 under addition, you have the numbers 1, 2, 0, 1, 2, and 3. And the Cayley table looks like this. You're just adding mod 4, 0, 1, and then finally 3, 0, 1, 2. So that's what the Cayley table would look like for Z4 under addition. And notice if you just rename them to A, B, C, and D, you get the exact same thing. So this is a group. I'll just do a little check mark. So that one is a group. Another one we've seen with 4 elements, since we're looking at a couple examples with 4 elements. So this one wasn't a group, this one was. We saw another one with 4 elements before. That was our symmetries of the rectangle. We can see that in a different way. If I look at addition, or sorry, not addition, multiplication mod. Actually, we'll get to that in a second. Let's first look at some groups, and then we'll look at the example I was trying to say that's like the Klein group. So one main example of groups are called the cyclic group. That's just Zn under addition. So Z4 was one of those, but for any n, you get a group under addition, and we call that the cyclic group. You can sort of see the cyclic nature, like each row is just a cyclic rearrangement of the rows above it. And the example I want to use for the Klein group is the group of units in Zn. So this is still multiplication mod, or this is still mod n, arithmetic mod n, but we look at multiplication. And remember that the only way you can get inverses is if the numbers are relatively prime to n. So for example, let's look at U8. So all the even numbers below 8 would not be relatively prime to 8, and so they wouldn't have an inverse. So we only focus on the numbers that are relatively prime to 8, so that's just 1, 3, 5, and 7. And so that's 4 elements, so we'll get another group with 4 elements. And if you do that multiplication mod 8, so of course 1 is still the identity, multiplying by 1 still gives you just 1. Well, 3 times 3 is 9, mod 8 is 1. 5 times 5 is 25, mod 8 is 1. And 7 times 7 is 49, mod 8 is 1. So you get that same structure where you get identities down the middle. Let's put the rest of the numbers here. 3 times 5 is 15, mod 8 is 7, so 7 again there. 3 times 7 is 21, mod 8 is 5, and 5 times 7 is 35, mod 8, which is 3. So you get the same numbers here. So notice these have the exact same structure, just rename elements to the numbers. And so this is another example of the Klein 4 group. So that anything that has this structure is, we would say, is isomorphic to K4, the Klein 4 group. Other examples with matrices, if you take all the n by n matrices that are invertible, you get a group. And the special linear group are elements of the general linear group where the determinant is equal to 1. And that's because of the fact, if you remember some linear algebra, the determinant of a product of two matrices is the product of their determinants. We'll actually prove that for 2 by 2s in a little bit. So you couldn't take, like if you wanted to create a group just naively and say, let's just take all the matrices that have determinant 2. It would have, well, I guess it wouldn't have an identity element, but it would be an associative thing. But it certainly wouldn't be closed, because if you took 2 matrices of that have determinant 2, well, their product would have determinant 2 times 2, which is 4. So it wouldn't be closed. But you can do that with determinant 1, because if you take 2 matrices of determinant 1, then their product will have determinant 1 times determinant 1. So it would also have determinant 1. Another example here, the quaternions. This is a generalization of complex numbers, where you have not just I, which is a square root of -1, but you have j and k, which are also square roots of -1. So you have 3 independent square roots of -1, and they interact with each other in different ways. So ij is k, jk is I, ki is j, but when you multiply them in sort of the not alphabetical order, you get the negatives. So a way of remembering this is if you put I, J, and K and just make little arrows. This tells me that I, J is K, KJ, or JK is I, KI is J. So when you multiply in alphabetical order, you just go around this little circle. But JI, for example, is -K. So if you go that way, you still get that, but with a negative sign. So if you go the other way around, you get the negatives. So it is not a commutative group, where, of course, the complex numbers are. So if you just had I, you'd be fine. But if you include these other roots of -1, then you get a non-commutative group, or what we call a non-abelian group. Here's an example where we define a new operation on a set, and we want to decide whether or not this is what we call an abelian group. So abelian just means it's also commutative. So we'll have to prove 4 things. We'll have to show that it's associative, we have to show it has an identity, inverses, and also commutative. We have to show that it's abelian. A little typo here. This should just be the set that we're looking at for our group is all real numbers except for the number -1. So just take the real number line, pluck out -1. Those are the elements that we're looking at. And the binary operation we're calling star kind of involves both addition and multiplication. It adds the 2 numbers together and then multiplies them, and then adds their product to that sum. So for example, 3 star 4 would be 3 plus 4 plus 3 times 4. So that's 7 plus 12, so that's 19. So 3 star 4 is 19. Well, we want to show that this is also a group. So let's go through each of the properties. So let's the hardest part, I think, will be to show that it's associative. Maybe not hardest, but the most tedious part is to show that it's associative. So I need to look at A star B star C and show that if I do the parentheses here, I get the same thing as if I put the parentheses there. So it's just a lot of work. So let's go through it. So first we do A star B, which is this. So this is A plus B plus AB, and then star C. And then to do this star, this whole thing will be like the A, and then the B will be like the C here. So but it might be easier to think in words. So the star adds them together and then adds their product. So I'm going to add these 2 together. And then add their product. Just be careful of the product. We're going to have to distribute that C. So when I do that, let's see, I'm going to do this in a systematic way. So I get A, B, and C. I get AB. And then I'm going to get AC. I'm going to get BC. And then I'll finally get ABC. So there's a nice sort of structure that you get when you multiply them together this way. So you get them all 1 at a time, all 2 at a time, and then you get 3 at a time. So that's just 1. Now let's look at the other way around. So if I do A star B star C, but do BC first, so that'll be A star, and then B plus C plus BC. And now, again, you add them together, and then add their product. I should get the same thing. I can see the ABC there already. I get the AB from here. I get the AC from here. I have the BC here. And then that times that gives me ABC. So these are equal to each other, so that means these 2 are equal to each other. Let's separate this off so we got enough room for everything else. The other parts are easier. The identity turns out to just be 0. If I do 0 star A, that gives me 0 plus A plus 0 times A, which is A. So it did operate with A and give me A back. If I do it the other way, A star 0, that's A plus 0 plus A times 0. That's still A. So it does act as an identity. Now, inverse is actually probably the only tricky part of this. Like doing associativity, sorry, I should put here that we did the identity. Well, it was a lot of work, but nothing actually difficult or clever needed to happen here. 0 as an identity, pretty easy to guess. But the inverse isn't that easy to guess here. And I would invite you to pause to see if you could come up with what the inverse would be. So you just have to imagine, like, if I wanted the inverse of A, I need to put something here for B that involves A, so that when I get all this out, I get the identity. So in other words, I get 0, because we just established here that 0 is the identity. Okay, if you had a chance to try that out, the answer turns out to be minus A over 1 plus A. And let's just verify that. So the star would be to add them together, and then to add their product. A times so this is just now normal algebra, so I just have to, well, I'll let you try it out on your own, but you should just get 0. Everything should just cancel out here. So that means the inverse of A, I'll just fit it up here, the inverse of A is actually just minus A over 1 plus A. And this is the only time that we actually needed the fact that -1 is not allowed. Notice if A was equal to -1, I would be dividing by 0 here, so there wouldn't be an inverse in that case. So as long as we don't include -1 in our original set, we will have an inverse. Okay. And then the last thing, so we've shown it's a group. So at this point, we know it's a group. But we also want to show it's an abelian group. So the last step here is to show it's commutative. But that's actually really easy. If I do A star B, this is A plus B plus AB, and then B star A would be B plus A plus BA, but those are clearly equal to each other. And they're equal because it's kind of a symmetric setup, and A plus B is the same as B plus A times B is the same as B times A, so it kind of inherits its commutativity from addition and multiplication being commutative. Okay. So we said that the general linear group is in fact a group, but we actually didn't show that it's closed yet. So in other words, what happens if I were to multiply two invertible matrices? Do I necessarily get another invertible matrix? And so the reason why that's true is because of this being true for determinants. It's actually true for any size square matrix, but let's actually prove it for 2 by 2 matrices. So if A is, let's say, A, B, C, D, and I'm not going to do all the algebra here, I'll just sort of set it up for you. E, F, G, H for B. Then when I multiply them together, this is matrix multiplication, so you do the row from A with the column from B, so A times E, B times G, and add those together, so AE plus BG is the first entry. AF plus BH, the next one. And you get CE plus DG, and then you get CF plus DH. So that's what the product of the two matrices would look like. And then the determinant of that product, well, determinant of a 2 by 2, you multiply here, subtract this product. So it's AE plus BG times CF plus DH minus CE plus DG AF plus BH. So that's what the determinant of AB looks like. Now I need to show that that's the same as if I did it this way, or if I multiplied the two determinants together. So the determinant of A is AD minus BC, and the determinant of B is EH minus GF. Now this is the algebra that I'll leave to you. Show that those two are equal, or in other words, multiply this out. Lots of canceling will happen, and then you sort of refactor it. Or you can multiply both of them out and just show that they're equal to each other. But the reason why this shows that it's closed is that the only requirement is that the determinant is not 0. So an invertible matrix just has a determinant that's not 0. So the determinant of AB, the product of A and B, is the determinant of A times the determinant of B. But since A and B are assumed to come from GL2, let's put that at the beginning. So if A and B are in GL2 of R, then neither of these have determinant of 0, so the product of two non-zero things is not 0. So that means the determinant of AB is not 0. So this implies that AB is in GL2R, which is what we wanted, to show that it's closed. So if you take two invertible matrices and multiply them together, you get another invertible matrix. You probably already know that from a previous course, but this is sort of more of a proof as to why. Next, if you fix the number of elements, you do get a finite number of possible groups in each case. So here we're looking at groups with 8 elements. And we want to construct 3 different groups. So we did see one example, Q8, is an example of a group with 8 elements. So let's write down what that was. Plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And with all those things, I'll just put the little circle here again, I, j, and k. That's how they multiply. And if you go around the other way, it's negative. Now, how do we know we have different groups? Well, generally that's a hard question if we had really large groups. But one quick way to tell that you have different groups from something else is looking at the order of the elements. So here, every element has order 2. Or wait, no, because I squared is negative 1, so to get back to 1, I have to take it to the 4th power. So we'll say every element has order less than or equal to 4. So I, j, and k and their negatives all have order 4. 1, of course, has order 1. That always has order 1. And then negative 1 has order 2. So you have an element of order 1, element of order 2, and then 6 elements of order 4. So if you find another group of 8 elements with different orders than that, then you clearly have a different group. Another easy one, a cyclic group on 8 elements. That's just addition mod 8. Well, 0, of course, has order 1, but 1 has order 8. So this has order 8. I have to add 1 to itself 8 times before I get wrapped around back to 0. So it's definitely different from Q8, just based on that alone. Okay, I did have an example where everything was order 2. If I look at Z2 cross Z2 cross Z2, so these are all the 3 tuples where each element comes from 0, 1, or 2, or you could think of these as just binary strings of length 3. So 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So that's 8 elements, of course. And they add component-wise. So like if I took 0, 1, 0 and added that to, say, 1, 1, 0, then that would give me, add the first component, it's 1, add the second one, mod 2, of course. I get 0, and then 0, 0 is that. So that's how they would add together. And this is really a shorthand. Each one of these, like 0, 1, 1, is actually the coordinate 0, 1, 1. Now here everything is, well, the identity is order 1, but everything else is of order 2. If you add any of these to itself, you get 0, 0, 0. So every element, or every, we'll say, non-identity element has order 2. So that's also different from the other ones. This, notice we kind of saw something like this already when we talked about the Klein group. Let's bring that back again. Like everything here had order 2 as well, and they're the symmetries of a rectangle. You could actually, and this is, you know, Z2 cross Z2. So that's another way to see it. This one would be symmetries of a rectangular box. So you have different, we think of this box as rigid, so I can't like squish it like when we talked about this symmetry here for the rectangle is flipping it through here. That's sort of flipping it through the third dimension, of course. So I can't flip, like try and cut it in half here and flip the two ends to each other. That would deform the box. Or you could think of that as rotating it through the fourth dimension. But if I think of it as a rigid thing, then I only have three things I could do. I could rotate it through the x-axis, the y-axis, or the z-axis. So each coordinate represents which one I'm rotating. So this would be not rotating it in the x-axis, but rotating it in y and z and seeing what you get. So this would be all the rigid symmetries of a rectangular prism or a box. We'll finish up this video proving some basic properties of groups. So when you define something like this, or a structure like this, when you define a group, you want to give properties that are enough so that other properties come from them. So like you could define a group where, where you say on the outset that the identity is unique or inverses are unique. But if they can be proven from other properties, then it's not necessary to include them in your definition. So it turns out all these things that we're going to show are things that we certainly want to have in a group, but aren't necessary to include as part of its definition. So first, the identity is unique. So uniqueness proofs usually go by first assuming they're not unique, there's more than one, and then showing that that's not true. So for our proof here, suppose we have two identities, so E and E prime are identities. Then let's imagine what happens if I multiply them together, or whatever the group operation is. Use that group operation. I'll put the little circle here. We're not always going to do that. We'll usually just concatenate. Well, since they're identities, I can think of, this one as the identity multiplying by the E. So that would give me just E. But I could also think of this as the identity acting on E prime, which would just give me E prime. But now, of course, I have E prime being equal to E. So trying to include more than one just kind of forces them to be the same thing anyway. So that means the identity has to be unique. Similar with inverses, they're unique. So again, suppose that some element G has two inverses. So G, an element of our group, has two inverses. And we'll give them names, G prime and G double prime. So one thing to do is to say, well, I want to take advantage of the fact that they're both inverses of G. So I'll create something that would create a combination of these three where I get to take advantage of that fact. So I'll put G, and then I'll kind of put G, the two inverses on either side. So I'll put G inverse on this side, G, one inverse on one side, one inverse on the other side. But this, since we're in a group, it's associative. So I could evaluate these two first, or I could evaluate these two first. So let's put the associative property here. So I'll put these in the same order. But here I'll do these two first, and in this one I'll put these two first. So I can evaluate this going either direction. So if I evaluate this way, since it's the inverse, it's the identity. So it's the identity times G double prime. So that, of course, is G double prime. If I go the other way, that's the identity again, because G double inverse is also an inverse of G. G prime E. And that's the identity, so that's just G prime. But once again, we have that these two are the same. So only one inverse. We saw this when we talked about functions. The inverse of a product, or of a composition of two functions, was those two functions, the inverses of those two functions, but in the opposite order. So same thing happens in general. And so if you compare this to a normal algebra thing, you would kind of distribute the -1, get A inverse, B inverse. And if things were commutative, that would be the same thing. But this is taking care that we might not have commutativity, which happens quite a lot in our groups. So how do you prove something like this? In words, we're saying the inverse of, so let's put this in words, the inverse of AB is B inverse A inverse. So how do I show that the inverse of something is something else? Well, multiply them together and see if you get the identity. So AB times B inverse A inverse. Again, I can use associativity to say I can rearrange the parentheses as long as I don't change the order. So I rearrange the parentheses this way. That's the identity. Identity times anything is itself, so I get A inverse, and that's just the identity. So that does prove that the inverse of AB is B inverse A inverse. And actually, it doesn't quite do it. It's 1/2 of it. You have to also show that if I multiply this in the opposite order, I get the same thing. But I'll let you try that. Next one's similar. We're looking at for the inverse of A inverse. So again, in words, the inverse of A inverse is A. Well, I just, again, have to show that when I multiply them together, I get the identity. So A inverse times A, well, we already know that that's going to be the identity. So again, and you have to show the other way as well, but that should be enough. Next one is about if you have linear equations, they have unique solutions. So AX equals B or XA equals B both have unique solutions for X. So there's a unique X in the group that satisfies those equations. Well, not both of them, but each one separately. So let's take the first one here. So if I have AX equals B, well, now we do algebra, right? Well, you would divide by A in a normal algebra class, but here we may not have division, so we're going to multiply by the inverse of A on both sides. And inverse of A times A is the identity, so I just get X equals A inverse B. Again, in a regular algebra class, you would just say that's B over A, but you might not have division. So we get a solution. How do I know this is a unique solution? So suppose I have another one. Suppose AY is also equal to B. I can do the same thing, right? I just multiply both sides by A inverse. And I get Y is A inverse B, but that's X. So there isn't a second solution. Any other solution you try and find is just going to end up being the same as that one. And I'll let you try this one as well. For that, you'd have to multiply again by A inverse, but on the right. And the last thing for this video, we'll look at cancellation laws. So right and left cancellation laws are true in groups. So what are they? Just says if you had AX equals AY, that you can cancel out the A and get x equals y. So it's something we do in algebra most of the time. Actually, we don't do that in algebra because we're scared that we might have 0. So, but if a is on the right, you still get that. So if we're talking about real numbers, this isn't true, because if you had 0 times x equals 0 times y, that doesn't mean x and y are necessarily the same. But in groups, this is true. And of course, in real numbers, it's true too, as long as a is not 0. And the proof, again, we'll just prove this one. I'll let you prove the other one. Is this similar to what we did in the last proposition? So you have ax equals ay, and you multiply by a inverse on both sides. Or not both, the left-hand side of each. And so, of course, you just get x equals y. So I guess, the reason why that doesn't work for real numbers, like we usually do in algebra, is because 0 doesn't have an inverse. You might be wondering, wait, does that mean real numbers aren't a group? Well, under multiplication, no. They are a group under addition. But to make it a group to make anything a group under multiplication, a lot of times you have to remove some things. So most of the time, you just remove the 0 to make it a group under multiplication. But other times, we saw an example already. Let's see if I can find it. Yeah, we're looking at U8, or UN in general. You just take out the ones that have common factors. So you include only the ones that are relatively prime. So I can't include everything from 0 to 7 here if I want multiplication. So I am taking out 0, but I also have to take out some other things as well. So it usually is the case that if you want to make something a group under multiplication, then you got to remove some stuff from it. Okay, so in the next video, we'll finish up chapter 3, looking at some more exercises and looking at the concept of a subgroup.